Tonight, we go through 8 theories about the universe that scientists published, verified, and then discussed very carefully. Not because the math was uncertain, but because where it settled was uncomfortable. Each one takes something that feels permanent and ends with it looking different. The physics beneath you, the continuity you trust in your own mind, the silence above the roof tonight. By the end of this video, you're going to understand exactly why the ground state of all known physics might not be permanent, why your memories are statistically more likely to be false than real, why every advanced civilization in the universe could be right here and completely invisible, and why the most disturbing result in quantum mechanics has no known flaw. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. Theory 1. The false vacuum. In 2012, a team of physicists ran a calculation they had been avoiding for 3 years, and it gave them the answer nobody wanted. The Large Hadron Collider had just measured the Higgs boson mass at approximately 125 billion electron volts. This was celebrated. It completed the standard model. It was described as one of the greatest achievements in the history of particle physics. What was not described, not in the press releases, not in the headline summaries, was what happened when the theorists plugged that number into the equations governing the Higgs field and asked a specific question. Is our vacuum stable? The Higgs field is not a metaphor. It is the quantum field that gives particles their mass, that gives matter the property of being matter. Every physical law that governs the universe hangs from it. The strength of the electromagnetic force, the range of the weak nuclear force, the particular mass values that allow atoms to form bonds, and those bonds to form molecules, and those molecules to form everything you have ever touched. All of it depends on the Higgs field sitting at its current energy value. The question is whether that value is the lowest possible one. Because if it isn't, if the current state is a local minimum rather than a global one, then the ground is not the ground, it is a ledge. And quantum mechanics, which governs how fields behave, does not allow ledges to be permanent. This is the false vacuum hypothesis. And the 2012 calculation placed our universe squarely in what the paper called the metastability region. Not clearly stable, not clearly unstable, balanced at the edge of an open question, with error bars that touch the stable region and also touch the deep metastable region, and no current collider capable of narrowing those error bars enough to say which one is true. The mechanism is not exotic. Quantum tunneling the ability of quantum systems to cross energy barriers they could not classically cross is not an edge case. It is the mechanism behind nuclear fusion in stars, the foundation of semiconductor technology, the reason alpha decay occurs at predictable rates in every nuclear physics experiment ever performed. It is a rule that operates at every scale, in every region of space, at every moment. If at any point in the history of the universe, anywhere in the observable cosmos or beyond it, a quantum fluctuation nucleated a bubble of true vacuum, the lower energy state, that bubble would expand outward at the speed of light. Not gradually, not with warning, at the speed of the fastest signal that physics permits, which is also the fastest speed at which any information about it could possibly reach you. Sidney Coleman, who spent his career on exactly this problem, reportedly said in later years that the false vacuum was one of those theoretical results where the appropriate response was a kind of enforced equanimity. The situation was either true or it wasn't, and there was other physics to be done. He continued working until shortly before his death. He never found the calculation to be wrong. Tonight, the sky looks exactly as it would look either way. The photons arriving from the direction of every star carry news of those stars as they were years or centuries ago, before any bubble could have formed, before any transition could have propagated outward from wherever it might have begun. The sky is always a record of the past. It cannot report the present, and the present is the only time the answer would matter. There is a particular way to understand vacuum decay that physicists find useful when they want to stop abstracting it and feel what it actually describes. The math, at this point, has been understood for decades. Coleman's equations are not contested. The mechanism is not in doubt. What is harder is the question of what it means, not in a scientific sense, but in the sense of what it means to sit inside a vacuum whose stability is unverified. On a night that looks exactly as it would look under any other conditions, what it means is demonstrated more clearly by the scenario than by any further discussion of the equations. You are outside at night. The temperature is comfortable. The stars are where they should be, fixed in their positions. The slow arc of the sky moving in the direction it always moves. Your body is warm. You are breathing at whatever rate you breathe before sleep. Somewhere, at a distance of perhaps several billion light years, a quantum event completes itself. A region of space roughly the size of a proton transitions to the true vacuum. The bubble is born. For the following billions of years, nothing changes for you. Light from the galaxies ahead of the bubble continues traveling toward you, carrying information about how those galaxies looked before the transition. You continue receiving that light. Those galaxies continue appearing in your sky. Your instruments register nothing unusual, because every instrument you have works by receiving photons, and the photons in front of the bubble have been traveling at full speed since before the bubble formed. They carry no news of what they left behind. The bubble expands. It crosses the space between galactic clusters. Stars and galaxies it encounters are not destroyed in any dramatic sense. They exist for one moment inside the old physics and the next moment inside the new one. And the structures that were stable in the old physics have no equivalent in the new. The transition happens below the threshold of any meaningful duration. At the moment, the bubble is 1 light second away from where you are lying. You have 1 second remaining. Not 1 second of warning. 1 second of existing. The bubble travels at light speed, and light takes 1 second to cover 1 light second of distance, and you are at the far end of that distance. There is no sensation of ending. The machinery that produces sensation is itself subject to the same transition as everything else, and the transition takes less time than any neurological process can resolve. One instant you are here. The next instant is not available. Here is the part that warrants the most attention. If the bubble exists and is traveling, it reaches you at the same moment it reaches the most advanced civilization in the observable universe. Assuming both of you are in its path, it reaches the most complex mind in the cosmos and the simplest hydrogen atom with equal indifference. The sophistication of the thing it encounters is not a variable in the physics. The bubble does not approach the powerful more slowly or give the intelligent more time. In most existential scenarios cosmologists discuss, there is an implicit asymmetry. Some things survive, some don't. There is suffering before the end. There is a before and an after. The vacuum decay scenario has none of these features. There is a before, and then there isn't. The asymmetry is as clean as any physical transition can be. The bubble is either out there or it isn't. The math doesn't resolve which. And the photons that left those regions of space before the bubble reached them are still traveling, carrying no message about what changed after their departure. From here, those stars still appear to shine. The second theory is different. It doesn't threaten the world from outside. It threatens the mind doing the looking. The phrase metastability region appears in a 2012 paper by 7 authors published in the Journal of High Energy Physics. The title is Higgs Mass and Vacuum Stability in the Standard Model at NNLO. It is not a fringe document. It is one of the most cited papers in high energy physics from that decade. That alone is worth pausing on. This is not a result from the margins of physics. It is a central, heavily scrutinized calculation that emerged directly from the most celebrated experimental result of the century. The Higgs discovery and the metastability problem are the same measurement. The paper that announced triumph and the paper that described the unsettling consequence were published in the same year by overlapping communities of physicists using the same data. The paper maps stability as a function of two measured quantities: the Higgs boson mass and the top quark mass. It divides the possible combinations into three zones. Stable, the vacuum will not decay on any physically relevant timescale. Unstable, it will decay quickly. Metastable, the decay timescale exceeds the current age of the universe by an enormous factor, but is not infinite. The measured values of both quantities place our universe in the metastable zone, close to the boundary with stable but not across it. The error bars overlap with the stable region. They also overlap with the deep metastable region. What looks like reassurance, we're close to the stable zone, is also true in the other direction. We're close to the deeply metastable zone. The data doesn't resolve, which is the correct interpretation. Here is what makes this different from ordinary scientific uncertainty. Most unresolved questions in physics are unresolved because we need better experiments. Better experiments are planned. The answer will come, but resolving the vacuum stability question requires measuring the top quark mass at a precision that no planned collider can achieve. The next generation of experiments might narrow the error bars. They are not expected to close the question. And there is an additional layer, one that gets less attention than the spontaneous decay calculation. Even if our vacuum is metastable, the spontaneous decay lifetime is calculated at roughly 10 to the 500 years. This is so large it is practically irrelevant. The universe will have done everything it can possibly do before spontaneous decay is likely from internal randomness alone. But the calculation assumes spontaneous, internal nucleation only. It says nothing about what Coleman called seeded decay. Transitions triggered by an external event, a neutron star collision at close range, a cosmic ray at the precise energy and angle to catalyze the transition locally. The probability of seeded decay is harder to calculate, and the numbers are less reassuring, and the calculations have not been completed in any satisfying way. Physicists do not generally discuss this at the level of public communication because there is nothing to be done about it. No engineering project addresses vacuum stability. No policy changes it. The appropriate response, practically speaking, is to work on the physics until the answer is known and to think about something else in the meantime. The second theory takes this to its logical next step. If we're uncertain about the ground, what about the mind standing on it? There is a specific comfort people reach for when they encounter vacuum decay, and it is worth examining because it reveals how we process this kind of knowledge. The comfort goes like this. The probability is vanishingly small on any human timescale. The decay lifetime is 10 to the 500 years. We are completely safe in any practical sense. And if it happens without warning and without suffering. So even in the worst case, the actual experience is brief in a way that eliminates most of what we normally think of as suffering. So there is nothing to worry about. This comfort is not wrong. On a practical level, it is entirely accurate. No existential risk framework assigns meaningful weight to vacuum decay. No civilization collapse scenario includes it. Every other threat, climate, conflict, pandemic, asteroid, deserves more attention by orders of magnitude. But here is where the comfort starts to reveal something else. The comfort is a performance of normalcy. It is what you say to return the conversation to ground that feels more manageable. What the vacuum decay calculation actually describes is not a threat in the usual sense. It is a description of what the ground state of physics is. And what the ground state of physics is precisely is this. The stability you are sitting inside right now is a local condition, not a universal one. It has persisted for 14 billion years and may persist for another 500 trillion, but it is not guaranteed. and it never was guaranteed. And the word stable, as physicists use it, means something categorically different from the word permanent as most people hear it. When physicists say the universe is stable, they mean stable within error bars, stable within the current framework, stable as far as we can determine. When most people hear the word stable, they mean something closer to, this will not be taken from us. Those are not the same word. The distance between them is not a flaw in communication. It is the actual content of the theory. You are resting on a foundation that physics can describe with extraordinary precision and cannot guarantee with absolute certainty. Not a threat, a description, and the description has been true for the entire history of the universe. You simply had not looked directly at it before tonight. There is one more dimension of this that is worth carrying into the next theory. The false vacuum is, in a certain sense, the most physically distant of the eight. It describes something happening at the level of quantum fields, at scales far below atoms, at energy levels far above anything in ordinary experience, across timescales so vast that no human institution has ever had to think about them. The threat, if it is a threat, operates at a completely different remove from the ordinary scale of a life. But notice what the false vacuum calculation required. It required a mind to perform it. It required consciousness embedded in this particular vacuum, using the mathematical tools this particular vacuum made possible to derive the specific result that the vacuum containing that mind might not be stable. The calculation is self-referential in a way that no measurement of a star or a galaxy is self-referential. It is the ground describing its own groundlessness. It is the laws of physics, applied by a being made of physics, producing the conclusion that the physics the being runs on might be temporary. That is not a small thing. That is one of the stranger positions that intelligence has ever found itself in. The second theory is stranger still, because it takes the mind that performed this calculation and asks whether the mind itself is any more stable than the vacuum it detected. Theory 2. The Boltzmann brain. The second law of thermodynamics describes how the universe moves. Closed systems left alone tend toward higher entropy, toward disorder. Heat flows from hot to cold. The coffee cools, the breath dissipates. This is not a preference of the universe, but a probability. Disordered states are simply more numerous than ordered ones, and systems that can change tend toward the more common configuration. The arrow of time, the irreversibility of events, the reason your life runs forward and not backward. All of it follows from the overwhelming statistical dominance of disorder over order. Ludwig Boltzmann understood this with more precision than anyone before him, and he also understood something that follows from it, which troubled him. Statistical mechanics describes probabilities, not prohibitions. High entropy states are overwhelmingly more probable than low entropy ones. But improbable events do happen. Order spontaneously assembles from disorder, the way that the molecules of air in a room occasionally all drift to one corner, not for any reason of principle, but because the laws of physics allow every configuration, and over long enough timescales, every allowed configuration occurs. This is ordinary physics. Boltzmann accepted it. What Boltzmann did not fully follow, and what later physicists did, is the question of what happens when you extend this reasoning to the question of minds, in an infinite universe with infinite time, or in any universe that reaches thermal equilibrium and then persists. Quantum fluctuations will eventually produce every possible configuration of matter. A scattered collection of atoms might spontaneously arrange into a protein into a cell into a brain. A full, functioning, conscious brain might emerge from random fluctuation, complete with a lifetime of memories, a sense of being a particular person in a particular place, a set of experiences that feel continuous and real and earned. That brain would exist for a fraction of a second before thermal equilibrium dissolved it back into disorder. But for that fraction of a second, it would have exactly the same experience that you are having right now, the same sense of a body, a history, a night, words being received. Here is what made this disturbing enough to be published. If the universe is old enough that Boltzmann brains can emerge by fluctuation, how many have emerged compared to how many ordinary minds arose through the long, slow process of stellar evolution, planetary formation, and biological development? The calculation, done carefully under the assumption of an infinite or near-eternal universe, suggests that Boltzmann brains vastly outnumber ordinary minds. The overwhelming majority of conscious experiences in the far future of an eternal universe are single flashes of false consciousness, complete with fabricated memories, surrounded by random matter dissolving within microseconds. If you are a typical mind in such a universe, if your existence is randomly sampled from all conscious experiences, you are almost certainly one of the brief ones. Your sense of having a history, of having slept last night and woken this morning and carried a life forward, is almost certainly fabricated, not a lie you are telling yourself. A quantum fluctuation that assembled, among other things, the precise neural architecture that generates the experience of having a history. The feeling of being continuous is not evidence of being continuous. It is exactly what a Boltzmann brain would feel. Descartes, in the 17th century, raised the question of how we can know the external world is real. He concluded that the act of thinking proved the existence of a mind, even if everything else was uncertain. I think, therefore I am. The thinking is the anchor. The Boltzmann brain hypothesis accepts that anchor. And then it dissolves everything attached to it. You are thinking. A mind exists because a mind is doing this. Descartes was right about that part. But a mind exists does not mean this mind has a history. The cogito proves the present moment. It says nothing about what came before it. If your brain emerged by quantum fluctuation 10 seconds ago, assembled by randomness into a complete and detailed architecture of false recall, it would be impossible from the inside to distinguish that from a brain that actually lived through the memories it contains. The memory of a specific morning, a specific room, a specific voice heard years ago. These are configurations of neural tissue. Neural tissue can, in principle, be arranged that way by fluctuation rather than by experience. The configuration would be identical. The experience produced by that configuration would be identical. There is no instrument in the brain that distinguishes fabricated continuity from real continuity, because such an instrument would require access to information the brain cannot have, namely, where its own architecture came from. This is what made the Boltzmann brain problem more than philosophical curiosity. It became a quantitative cosmological constraint. If a model of the universe predicts that Boltzmann brains become the dominant form of consciousness at some point in cosmic history, physicists consider that a strike against the model. Not because false minds are obviously impossible, but because if the model were true, our existence as ordinary minds would be incredibly unlikely, which means the model fails to explain what we actually observe. Alan Guth, who developed inflation theory, has argued that inflationary cosmology needs modifications specifically to avoid predicting Boltzmann brain dominance. Don Page, who worked with Hawking, published several papers in the 2000s, arguing the problem was serious and unresolved. Sean Carroll has described it as one of the genuinely open questions in modern cosmology, and here is the specific turn that makes this different from other philosophical problems about certainty. The debate is circular in a way that has no exit. If you are a Boltzmann brain, your assessment of the probability that you are a Boltzmann brain is itself a fabrication. Your ability to reason about cosmological implications was assembled by fluctuation, not trained by actual engagement with the physical world. Or you might be a brain whose false architecture happens to produce the pattern of reasoning that concludes it is probably real. The feeling of reasoning well is not evidence of reasoning well. It is also what a Boltzmann brain would feel when physicists find a theory leading toward absurdity. The standard move is to identify where the absurdity enters the chain of reasoning. The Boltzmann brain problem has been studied with this intent for roughly 2 decades, and no clean exit has been found. The exits that have been tried illuminate why the problem is structurally unusual. One approach argues Boltzmann brains cannot form even in infinite time because the quantum fluctuations required are too improbable, but this fails immediately. The same statistical mechanics that produces Boltzmann brains also produces the entire ordered history of a universe. And our universe demonstrably exists, which means the machinery for extremely low probability fluctuations is real and operational. A universe that can fluctuate into existence can certainly fluctuate a brain into existence. A second approach argues that inflationary cosmology produces so many ordinary observers that even in the long run, Boltzmann brains don't dominate. Various inflationary models claim to resolve this. The difficulty is that the models are being constructed to avoid the Boltzmann brain problem rather than predicting a solution from independent principles. When you tailor a physical model to avoid an uncomfortable conclusion, the avoidance is doing the work, not the physics. A third approach uses the anthropic principle. We observe an ordered universe because disordered false universes produce observers who can't reason reliably and therefore can't ask this question. This also fails because a Boltzmann brain, assembled with false memories of growing up in an ordered universe, can absolutely ask this question. A Boltzmann brain with a false physics education will run the Boltzmann brain calculation and conclude, with high confidence, that it is probably not a Boltzmann brain. The impeccable reasoning is part of what was fabricated. Sean Carroll, who has written extensively on this, describes it as a problem that constrains which cosmological models are acceptable rather than a problem that has been solved. The fact that it hasn't been resolved is not a sign that physicists gave up. It is a sign that the problem is hard in a way that doesn't yield to the usual tools. You are almost certainly not a Boltzmann brain, because the reasoning that produces almost certainly is exactly the reasoning a Boltzmann brain would produce. The loop is not closed. It is managed. One of the genuinely underexplored aspects of this theory is what it implies. Not about whether you are a Boltzmann brain, but about what the experience would be like from inside. A Boltzmann brain is not the brain you have now, sitting in a body, receiving sensory information from an environment. It is a brain that assembled complete with a full internal model of a body, a history, an environment. All of it generated by the neural configuration itself, not by actual sensory experience. The brain arrives into existence already believing it has been alive for decades, already carrying specific memories of specific people, specific rooms, specific mornings, and specific regrets. Those memories would feel no different from the ones you are drawing on right now. The texture of a childhood room, the sound of a particular voice, the quality of light on a specific afternoon years ago. A Boltzmann brain would have these fully formed immediately upon coming into existence. They would not feel like fabrications. They would feel like memories, because the neural structures underlying them would be structurally identical to the neural structures underlying real memories. This is the precise point where the theory becomes difficult to dismiss. It is not that a Boltzmann brain would be confused or obviously wrong in some detectable way. It would be perfectly confident. It would have the same degree of certainty about its past that you have about yours. It would trust its memories, make plans, form connections between its experiences, and behave in every measurable way like a mind with genuine continuous history. And then, in a fraction of a second, the fluctuation would dissolve. The experience would end without the brain knowing it had begun. From the inside, the experience would not feel temporary. It would feel exactly like this. Like the present moment feels, receiving these words, in a room with whatever particular quality the air carries tonight. The only way to distinguish it from your current experience is to know whether your past is real. and there is no instrument in your current experience that provides that knowledge. What comes next doesn't question what you are. It reframes what happens to you. There is a practical implication inside the Boltzmann brain hypothesis that doesn't get discussed as often as the metaphysical ones, and it is in some ways more immediately unsettling. If the possibility that you are a Boltzmann brain cannot be ruled out, if no observation from inside the mind can confirm or deny it, then every reasoning process you engage in is operating on an unverifiable foundation. Not a foundation that is probably wrong, a foundation that is unverifiable in principle. The chemistry of your neurons, the patterns of activation that produce what you call reasoning, the memories that inform your priors and shape your inferences. All of it could be the output of a mind assembled with false inputs, and you would not know this from inside the process of reasoning. This is not a recommendation to doubt everything. The practical advice to doubt everything leads nowhere useful, and the architects of skeptical philosophy understood this. The Boltzmann brain hypothesis doesn't recommend universal doubt. It identifies a specific gap between the experience of reasoning reliably and the actuality of reasoning reliably, and it provides a physically coherent account of how that gap could exist without being detectable. Scientists who take this seriously don't conclude that science is impossible. They conclude that the problem must be resolved at the level of cosmological models rather than individual reasoning. If our cosmological model implies Boltzmann brain dominance at any point in cosmic history, the model is likely wrong, not because we can inspect individual minds, but because the distribution of minds it predicts is incompatible with what we find ourselves to be. The model fails because we observe a world consistent with having evolved normally, and in a Boltzmann-dominated cosmology, that observation would be overwhelmingly unlikely. This is the best available response. It shifts the burden from individual epistemology to cosmological model selection, but it leaves intact the basic structure of the uncertainty. The trust you place in your own cognitive processes rests ultimately not on any direct inspection of those processes, but on your confidence in the cosmological model that predicts they are reliable. And that confidence is itself a product of those processes. There is a practical version of this that is worth sitting with. When a scientist evaluates whether a cosmological model is good, she does so by checking whether the model's predictions match observations. But her ability to check that, her ability to identify which observations are relevant, to perform the comparison correctly, to judge what counts as agreement and what counts as discrepancy, depends on the reliability of the very faculties the model is supposed to be validating. The model is used to validate itself, not through a flaw in the method, but through a structural feature of the problem. There is no observation that exists outside the observer. There is no check that the checker can perform on itself from the outside. Don Page, who worked with Hawking on black hole thermodynamics and has published extensively on the Boltzmann brain problem, has described this as one of the situations in which physics arrives at a genuinely foundational constraint. Not a gap in the current theory that a better theory will fill, but a permanent limitation on what any theory can verify about itself. A theory of the universe is written by minds inside the universe. The truth of the theory depends on those minds being reliable. The reliability of those minds is what the theory claims to address. The circularity is not a loop that needs to be broken. It is the shape of the problem. It is, in a sense, the shape of any epistemology. The recognition that knowing happens from somewhere, not from nowhere, and that the place you know from is also part of what you're trying to know. The loop is not closed by science. It is managed. The third theory doesn't question your reliability. It tells you what happens next, and the answer is worse than you expect. Theory 3, quantum immortality. Hugh Everett III published what he called the relative state formulation of quantum mechanics in 1957 as his Princeton doctoral dissertation. His advisor helped him tone it down before publication. Whatever it originally proposed, what the toned-down version still implied, if you followed the logic, was that the universe does not select a single outcome when a quantum measurement occurs. It contains all outcomes simultaneously, each in its own branch of a universal wave function that never collapses. In the usual formulation of quantum mechanics, when you measure a particle in a superposition of two states, the act of measurement causes the wave function to collapse into one result. You get one outcome. The other result doesn't happen. Everett's formulation says the other result does happen in a branch of reality that is real, physical, and now inaccessible to you. The universe literally contains both histories, evolving into a superposition of two distinct paths forward. The many worlds interpretation is not fringe physics. It is one of the most seriously debated interpretations of quantum mechanics, favored by a significant fraction of professional physicists, and considered the mathematically cleanest formulation by those who prefer not to invoke wave function collapse as a primitive concept. Steven Weinberg discussed it seriously. Sean Carroll advocates for it. David Deutsch built his entire computational philosophy on it. If the many worlds interpretation is correct, then the following is also true. Every moment in which a physical event could either kill you or not kill you produces a branch where you died and a branch where you survived. The cosmic ray that might have caused the cancer that developed in another version of you. That branch exists. The car accident that almost happened. In that branch, it did. The random cellular malfunction that occasionally becomes a tumor. In many branches, it did. In this branch, the branch in which you are receiving these words, it did not. Quantum immortality follows directly from this. From your first-person perspective, the perspective of the mind that continues to experience things, you always find yourself in the branch where you survived, not because survival is guaranteed, because the branches where you did not survive are by definition not occupied by your continuing first-person experience. You can only ever find yourself alive, because finding yourself anywhere requires being alive to do the finding. This sounds like a comfort. It is not a comfort. Consider what the structure is actually saying. It is not saying that you are protected. It is not saying that the universe cares whether you continue. It is saying that the subset of futures you can ever observe is, by definition, the subset in which you are alive to observe them, and that this selection, applied continuously across every branching point in your life, produces the appearance of extraordinary luck without the substance of it. You are not lucky. You are filtered. Every version of you that died is simply not available as an observer. The one observing now is the residue. The difference between being lucky and being filtered is not semantic. A lucky person lives because something external intervened in their favor. A filtered observer lives because the alternative observers are not present to report. Luck implies the possibility of failing. The filter doesn't fail. It simply removes the instances of failure from the set of available perspectives. From inside that set, the removal is invisible. Every instance that remains believes itself to be continuous, to have survived through some combination of chance and circumstance. None of them know what fraction of the original distribution they represent. Under many worlds, the answer to that question is a very small fraction, and it gets smaller as time goes on. The horror of quantum immortality is not that you die, it is that you can't. Follow the logic. In every quantum branching event where you could have died, you didn't. From your perspective. This holds not just for unlikely accidents, but for every biological process in your body. Cancer, infection, organ failure, the slow accumulation of cellular damage that normally terminates lives in the 7th or 8th decade. In each case, there exist branches where the outcome went differently. And in those branches, you are not available to observe anything. The branch you always find yourself in is the one where the outcome did not go that way. Max Tegmark, the MIT physicist who published the original quantum suicide paper in 1997, noted that the implication is straightforward and profoundly disturbing. Under many worlds, you are immortal, not because anything protects you, but because the branches where you die are inaccessible to you. The first-person experience of being alive continues indefinitely, into increasingly improbable configurations of survival. Your body will age. Every physical process that normally terminates a life will, in the branches you inhabit, produce some outcome that does not terminate yours. This does not mean the outcomes are good. It means they continue. The branch where the disease progresses, but the specific configuration of cells produces a spontaneous remission. That branch exists, and you are in it. The branch where every reasonable expectation of your death is met with some increasingly improbable exception. That is the sequence of branches you trace through your life. At some point, the branches you inhabit become very sparse. Most versions of the universe have already moved on without you, because most versions of you have died by the normal calculations of physiology. But there remains, always, at least one branch where you are still here, older, in a world populated by people who watched you outlive all expectations in a physical condition that only the rarest biological outcomes could produce. Everett, according to his daughter's account, believed in quantum immortality and told her she need not fear death because she would always survive in some branch. She found this less comforting than he intended. The theory keeps your first-person experience running. It says nothing about the quality of that experience. The branches that persist are defined only by the condition that you are there. Everything else, the social world, the people, the civilization, has no equivalent guarantee. Tegmark's paper was partly exploring the limits of the many worlds interpretation by following quantum suicide to its logical conclusion and noting that the conclusion was uncomfortable. Subsequent readers pointed out that uncomfortable conclusions do not necessarily indicate false premises. The logic was valid. The premise was not experimentally ruled out. The conclusion therefore had to be taken seriously, at least until someone found the actual error. No one has found the actual error. One objection holds that the many worlds branches are not all equally real. That wave function amplitude determines how physically substantial a branch is. And very low amplitude branches are in some sense barely real. Under this view, your continued survival in increasingly improbable branches constitutes a kind of attenuated existence rather than genuine continuity. The problem is that this objection requires an interpretation of what wave function amplitude means for experience, and no satisfying account of this exists. The branches are all there. The math doesn't make some of them less real in any verifiable physical sense. Another objection holds that many worlds might simply be false. If Copenhagen is correct, if wave function collapse is a real physical process, then branching doesn't happen and quantum immortality doesn't apply. You will die normally. The problem is that no experiment can currently distinguish between these interpretations. They make identical predictions for every measurement we know how to perform. The question of which interpretation is correct is, at present, not answerable by physics. So the theory floats above the experimental record. If many worlds is correct, you will outlive everyone you know in a sequence of increasingly unlikely branches for as long as the physical universe supports minds. If it is incorrect, you will die normally. There is currently no way to know which is true, and the moment you find out, if you find out, will only be interpretable from inside the branch you're in. Hugh Everett died in 1982 at 51 of a heart attack. He had requested that his remains be disposed of as trash. His daughter struggled with his absence and the weight of his theories throughout her life. She died by suicide in 1996. She left a note saying she hoped to find him in a parallel world. The theory gives no indication of whether that is possible. There is a side of quantum immortality that is rarely discussed, because the focus tends to fall on the branch where you survive, on what it means to be the persistent thread of first-person experience running through increasingly improbable configurations of the world. But the branches where you died are also real. Under the many worlds interpretation, They are as real as this one, as fully physical, as completely inhabited by the people who knew you and the world that continued after you were gone. In those branches, everything went on. The room you were in continued to hold its furniture, its particular quality of light, its temperature. The people who cared about you moved through the aftermath of your absence with whatever combination of grief and adjustment and eventual adaptation people move through. The world did not pause, and in the vast majority of those branches, the version of you that could have read these words tonight is not here. The version of the world that contains you is the rare one. Across the full branching structure of all the quantum decisions that have been made in the course of your life, the branches where you are alive are the minority. The branches where the world continued without you represent most of what, under many worlds, is considered to be real. You cannot experience those branches because experiencing anything requires being alive to experience it. But they exist, and the people in them are as real as you are, and they are experiencing whatever they are experiencing in a world that you are not in. This is the part of the theory that Everett himself seems to have avoided dwelling on. The focus on immortality is, in a sense, the more bearable frame. The complete picture is simpler. In most of the real world, in most of the branches that currently exist, you are already gone. Tonight is not common. Tonight is one of the rare ones. The fourth theory takes this further. The first three threatened what you are, what you remember, and what happens to you. The fourth one is more precise. It threatens what you're allowed to know about your own danger. It is a theory about why the evidence you have access to is, by design, the worst possible evidence for the question it's supposed to answer. Theory 4. The anthropic shadow. Selection effects are a standard concern in scientific methodology. They describe how the act of observation shapes what can be observed. If you survey people leaving a hospital and ask whether they've been sick recently, you will overestimate illness prevalence in the general population. Your sample is biased toward people with reasons to be in a hospital. The data is real. The inference from it to the general case is distorted. The anthropic shadow is a selection effect of a different order, one that operates not on a study but on the entire history of life. And that bias is not a sample of observations but the very fact that observation is possible at all. Any observer who exists must exist in a history where they survived. This is tautological. If you didn't survive, you're not observing anything. But the tautology has a non-trivial implication. Events that would have eliminated all observers leave no trace in the observational record of any observer. By definition, not because they didn't happen, but because the histories in which they happened don't contain observers. Suppose there is a class of events, civilizational scale catastrophes, that periodically occur in the galaxy and kill all complex life in their vicinity. In histories where such an event occurs before intelligence develops, there is no intelligence to observe that it occurred. In histories where it occurs after intelligence develops but before the intelligence becomes spacefaring, the intelligence is gone and cannot report. The information is lost. The histories that contain observers capable of doing risk assessment are, by selection, precisely the histories where none of those events have occurred yet. And the word yet carries the full weight of the problem. Milan Cirkovic and Vukotic published a paper in 2008 formalizing this as the anthropic shadow. They argued that our estimates of near-Earth impact frequency, gamma-ray burst risk, and other civilizational threats were systematically biased downward, not because our measurements were wrong, but because the measurements are made by observers whose existence selects against having observed the most dangerous outcomes. We exist. This seems like evidence that the universe is safe for things like us. It is not evidence of that. It is the minimum requirement for us to be having this conversation. The naive interpretation of our survival so far is optimistic. We exist, which means nothing has killed us, which means either there is nothing capable of killing us, or the things that are capable of killing us happen rarely enough that we've gotten lucky so far. Under this interpretation, our existence is moderate evidence that the universe is not particularly dangerous for the kind of thing we are. The anthropic shadow inverts this inference entirely. The more dangerous the universe is, the more frequently catastrophic events occur, the more strongly any surviving civilization is selected for having been lucky rather than for being in a genuinely safe environment. A civilization that exists in a universe where catastrophic events occur every few million years will look exactly like a civilization that has been lucky, because it has been, not because it is safe. Critically, the more dangerous the universe is, the larger the fraction of observers who are in the situation where a catastrophe is imminent, because most of the histories that have survived this long are ones where the catastrophe hasn't happened yet, rather than ones where it genuinely can't happen. In a universe with a high rate of civilizational catastrophe, the average surviving civilization is always close to its end. It just doesn't know this, because knowing it would require observing it. And observing the catastrophe that ends you is not compatible with surviving to update your risk model. The practical implication is sharp. Any risk assessment that begins with, well, we've been here for 100,000 years and nothing catastrophic has happened, so the risk must be low, is already compromised at the foundational level. The 100,000 years of not dying are not evidence of low risk. They are the minimum required for this conversation to be happening. In a universe where most civilizations die within 100,000 years of reaching technological capacity, the civilizations that survive 100,000 years look exactly like us. And they are, statistically, close to the event that ends them, because that is what the distribution looks like from inside. We cannot know where on that distribution we sit. The structure of the problem prevents us from knowing. There is a specific version of the anthropic shadow that applies to the silence of the universe. The usual framings of the Fermi paradox tend toward two poles. Either intelligent life is genuinely rare, or intelligent life is common, but civilizations reliably destroy themselves before becoming spacefaring. The anthropic shadow adds a third layer, one that doesn't require civilizations to be rare or self-destructive. Suppose there is a class of events that reliably destroys intelligent civilizations, distributed through the galaxy at a frequency, implying most civilizations are destroyed before they develop interstellar communication. Under ordinary reasoning, we would expect to see evidence of this. Destroyed or silenced civilizations, signals that suddenly cut off, some record in astronomical data of the events that did the destroying. We see none of this. Not because the events don't happen, because the events that happened left no surviving civilization capable of telling us about them. Every civilization destroyed by the event left no record. The galactic neighborhood looks quiet because the civilizations that would have been our predecessors in communication are not here to communicate. This is not the same as the Great Filter. The Great Filter is an event or process that eliminates civilizations from within. A technology they develop, a threshold they fail to cross, a choice they make. The anthropic shadow describes elimination from without, by physical events that have nothing to do with the civilizations they destroy. The distinction matters because the Great Filter is something we might identify and avoid. The anthropic shadow, if it describes physical catastrophes, is not avoidable by any change in behavior or wisdom or self-restraint. The silence of the universe is therefore not reassuring. It is precisely what the dangerous universe would look like from inside a surviving civilization. The civilizations that would have been loud, that would have filled the radio spectrum, that would have sent probes, were eliminated before they got the chance. They are not here. What the anthropic shadow does, ultimately, is remove the flaw from underneath standard risk reasoning. In most domains, risk can be estimated from historical data. The frequency of earthquakes above a certain magnitude is estimated from geological records. The probability of a pandemic is estimated from the frequency of past outbreaks. The risk of a technological accident is estimated from near-miss incidents and failure rates in previous deployments. This works because the historical data contains the relevant events in some proportion that reflects the actual underlying rate. For existential risks, events that would end the ability to gather any more data, this method breaks. The events that ended civilizations are, by selection, absent from any surviving record. The civilizations that could have recorded them were themselves ended by them. The absence of evidence is not evidence of absence. It is evidence of selection. The strange implication is that we are, in a precise sense, the worst possible observers for assessing our own safety. Our existence is not a random sample from all possible histories. It is a sample from the specific subset of histories in which nothing existential happened yet. That subset may be common, meaning the universe is broadly safe, or it may be rare, meaning the universe is broadly dangerous, and we are an exception. These two possibilities look identical from inside. There is currently no method known, none proposed in any serious framework, for distinguishing between them using observations made from within the shadow. The shadow is definitionally opaque. To see past it would require observing the civilizations that were ended, which requires being them, which is not an available experimental option. This is where the theory leaves us, in a present that feels stable, measuring a past that was survivable, with no way to determine whether the stability is a property of the universe or a property of how we got here. The specific feature of this that distinguishes it from other forms of uncertainty is that it gets worse as the universe becomes more dangerous, not better. In a safe universe, surviving is evidence of being in a safe universe, a genuine signal. In a dangerous universe, surviving is also evidence of being in a safe universe, not a signal but the minimum condition for asking the question. The two cases look identical from inside. The more dangerous the universe is, the more it looks safe to the survivors. Safety and extreme danger produce the same observational signature when viewed from the only perspective available to an observer, the perspective of having survived so far. What the anthropic shadow ultimately describes is a wall between us and knowledge of our own situation. Not a wall built by ignorance, not a wall that better measurement will dismantle, but a wall built into the logic of what it means to be an observer embedded in a universe that can destroy observers. To know the true rate of civilizational catastrophe in the galaxy, you would need to observe the catastrophes that happened, including the ones that happened to civilizations capable of making exactly that observation. Those observations do not exist, not because the catastrophes did not happen, but because the observers they ended never filed the report. The fifth theory changes the subject. It doesn't threaten you, it threatens what you know, and it does it on a timescale that makes everything else look brief. Theory 5. The Last Stargazer. In 1998, two independent teams of astronomers measuring distant supernovae found something their data could not explain without revising the entire standard model of cosmology. The supernovae were too dim, by a statistically significant amount, that pointed in a specific direction. The universe was not decelerating, as gravity predicted. It was accelerating. Something was pushing the expansion of space itself to go faster over time, not slower, with no known physical process capable of halting it. That something was named dark energy, and it constitutes approximately 68% of the total energy content of the universe. Not dark matter, not any known form of matter or radiation, as best as current physics can determine. A property of space itself, energy that exists in empty space and exerts a repulsive effect at cosmological scales, growing in influence as the universe expands and producing a runaway acceleration that has no known end state. The discovery earned the 2011 Nobel Prize in Physics. It also set a clock running, in the background, beneath all of cosmology, counting down toward a state in which the observable universe becomes smaller, not larger, from the perspective of any given point. The mechanism is straightforward. As space expands, distant objects recede. The more distant the object, the faster it recedes, because more expanding space lies between you and it. At approximately 46 billion light-years from Earth today, objects are receding so fast that light from them can never reach us. This is the cosmological horizon, not a wall but a boundary beyond which the recession velocity exceeds the speed of light, which is possible because the recession is not motion through space but expansion of space itself. Here is what dark energy does to that horizon over time. As the expansion accelerates, the horizon contracts from the perspective of any given galaxy. Objects visible today will eventually cross the horizon and become permanently unreachable. Not because they moved away, but because the expanding space between them and us grew faster than light can cross it. Today we can observe approximately 2 trillion galaxies. In 150 billion years, roughly 10 times the current age of the universe. Most of those galaxies will have crossed the horizon. In 2 trillion years, even the local group will have merged into a single giant elliptical galaxy, surrounded by absolute emptiness. Any civilization in that galaxy will look at the sky and see nothing but their own stars. This alone would be a kind of loneliness that is difficult to hold. What it does to their science is worse. To understand what this means for any future civilization, consider what those civilizations will lose. Every conclusion in modern cosmology depends on observing other galaxies. The measurement of the Hubble constant, the rate of universal expansion, requires observing galaxies at different distances and measuring their recession velocities. The evidence for dark energy comes from Type Ia supernovae in distant galaxies. The cosmic microwave background, the thermal remnant of the early universe, and the primary evidence for the Big Bang will by that point have redshifted into frequencies too long to detect with any physically realizable antenna. Nearly all the evidence that allows cosmologists today to reconstruct the history and composition of the universe requires observing things far outside our own galaxy. In 2 trillion years, that evidence will not be difficult to find. It will not be hidden. It will be physically gone, redshifted to wavelengths so long that the photons carry essentially no information. The galaxies that provided the data will be beyond the cosmological horizon, their light permanently cut off. Any civilization that arises then and looks at the sky will see a single large galaxy, their own, surrounded by darkness. They will conclude they are alone. They will measure the stars in their galaxy and deduce from stellar physics that the universe is a few billion years old. They will have no evidence of inflation, no evidence of dark energy, no evidence of the billions of other galaxies that once populated the observable universe. If they are careful scientists, and suppose they are, because they have all the patience that 2 trillion years of evolution can produce, they will construct the best model their data allows. That model will be wrong in the most fundamental possible way. The universe will be hundreds of times older than they estimate. It will be incomparably larger than anything they can observe. The laws of cosmology they develop will be internally consistent, empirically supported by everything they can observe, and will describe a universe that does not exist. Abraham Loeb at Harvard noted in a 2011 paper that we live in a privileged era, a specific temporary window in cosmic history when the evidence needed to understand the universe at its largest scale is still available. Future civilizations will not have this. The data will be gone, replaced by silence, and the silence will be indistinguishable from what the universe would look like if it was small, young, and alone. There is a specific quality of loss here that is different from the other theories. The false vacuum threatens everything at once, without warning. The Boltzmann brain threatens the integrity of your own mind. Quantum immortality threatens you with a form of life that makes conventional mortality look manageable. The anthropic shadow removes your ability to assess your own danger. These operate on the present. The Last Stargazer is a threat that operates in the long future, not on you, but on minds that do not yet exist. In a universe that has grown old in ways that make the present universe look young. And what it takes from them is not physical safety. It is epistemic safety, the ability to know where you are and how you got there. Those future minds will arise inside a galaxy that is warm and bright by the standards of what surrounds it. They will develop science. They will ask the questions that intelligent things ask. What are we made of? How did we get here? Where does this end? They will build instruments, gather data, reason carefully about what the data means, and the conclusions they reach will be supported by everything available to them. And they will be wrong, comprehensively, foundationally, irrecoverably wrong. Not because they are not intelligent, but because the universe removed the evidence before they arrived. This is the most complete version of a moment being erased. We don't erase when we die. We erase when the record that proves we existed can no longer be read. In 2 trillion years, the universe will still be here. It will simply have no way to tell its own story. If there is any form of communication capable of spanning cosmological time, any archive, any physical encoding that survives the cooling of the universe, the transmission of what we currently know about cosmology might constitute the most meaningful act of preservation in the history of intelligence. Not because it is true forever, but because it will be irretrievable from the observable universe by the time it is most needed. We know this now. The universe is still telling its story. The last chapter can only be written in this era before the library closes. To say we live in a cosmologically privileged era is to say that the universe is currently in a specific window, one that will close, that is closing, that has been closing since the first stars formed and will not reopen once the last distant galaxy crosses the horizon. During this window, and only during this window, can an observer at any point in the universe look outward and see evidence of its true scale, its true age, its true history. We are, right now, in that window. We know it will close. Knowing you live in a cosmologically privileged era sounds like it should feel like privilege, like standing at a promontory with a view that will vanish, aware of the quality of the light before the cloud moves in, feeling the urgency of the unrepeatable. That is not what it feels like. The window is too large and human lives are too short, and the closing is too gradual for the loss to register as loss in any lived sense. We know the window is closing. We know it matters. We do not rush. The urgency is purely mathematical. The human response to it is, predictably, almost nothing. What is strange about this knowledge is that it cuts against a deep assumption underneath all of science, the assumption that the universe will continue to be available for study, that whatever we don't figure out today can be figured out later, by someone else, with better tools. That assumption is not generally true. What future cosmologists can know about the universe is bounded by what the universe is still willing to show at the epoch they inhabit. What we know now, what the evidence available to our instruments can tell us, is therefore not merely interesting. It is potentially irreplaceable. The microwave background data currently stored in archives represents knowledge that cannot be reconstructed once the photons carrying it have redshifted into undetectability. The recession velocities of galaxies currently beyond our horizon are measurements that cannot be made by any civilization arising after those galaxies have crossed the threshold. The past is not recoverable by going backward. In cosmology, going backward means measuring the light that is still, right now, arriving from it. When that light is gone, the past is gone in a way that no archive and no computation can fully restore. We are in the window. It is closing slowly, and it will remain open far longer than any civilization has so far existed. But it is closing, and it has always been closing. And the universe will continue this process with complete indifference to whether anyone remains to notice. There is a version of this problem that has a possible, if partial, answer. The evidence that will be gone in 2 trillion years is physical. Photons traveling through expanding space, eventually redshifting into undetectability. Physical evidence cannot be preserved against the expansion of the universe. The photons cannot be slowed, the expansion cannot be halted, but knowledge can be encoded. The content of cosmological understanding, the specific numbers that describe the size and age and composition of the universe as best we currently know it, is not itself a photon, it is information. And information can, in principle, be preserved in forms more durable than the physical substrate from which it was derived. This is not a trivial distinction. It is the distinction that libraries exploit and archives depend on. The scrolls of Alexandria are gone. The knowledge some of them contained survived, in copies, in translations, in quotations, embedded in other texts that outlasted the originals. The physical artifact is not the same as the content it carried. What we know about cosmology right now, in this window, constitutes a body of knowledge that will become impossible to derive from observation at some point in the future, not soon, in 2 trillion years, but impossible. Whatever civilization exists then, lacking the record we could create now, will be permanently unable to reconstruct it. Abraham Loeb has suggested, only half metaphorically, that the most important scientific project of the current epoch may be the creation and preservation of a cosmological record, not for any civilization that currently exists, but for civilizations that will arise after the evidence is gone. A message to the future, encoded in the most durable physical substrate available, containing the essential conclusions of observational cosmology. The universe is large, it is old, it began in a hot, dense state. It is mostly dark matter and dark energy. It is populated by hundreds of billions of galaxies you can no longer see. We are in the position of someone who knows something the next generation will not be able to learn on their own. The window is open. The evidence is still here. The record can still be made, whether we choose to make it. And whether the making will survive the intervening trillions of years is genuinely open. The universe offers no guarantees on any of it. There is also the question of what form such a record could take. The physical substrates we use for information storage, magnetic media, silicon, paper, optical discs, are durable on the scale of centuries or, at best, millennia. 2 trillion years is not 1,000,000 times longer than that. It is 1,000,000,000 times longer. The challenge of encoding information in a form that persists across that span is not an engineering problem that current or near-future technology can address. The atoms of any physical medium will decay, rearrange, become indistinguishable from background entropy long before the window closes, and the need becomes acute. The most durable physical inscriptions we know of are geological. The record of nuclear isotope ratios in ancient rock, the orbital signatures of extinct planetary bodies encoded in the gravitational dynamics of surviving ones. Some researchers have proposed, only partly in jest, that the most reliable way to leave information across cosmological time might be to encode it in the large-scale structure of matter and gravity rather than in any local physical medium. Whether this is even theoretically possible is not settled. Whether it would survive the processes that rearrange galaxies on timescales of hundreds of billions of years is not known. What is known is the urgency that the last stargazer creates, if you take it seriously. The record cannot be made in 2 trillion years, when it will be needed. The record cannot be made in 1 trillion years, when most of the galaxies will have crossed the horizon. The record can only be made now, in this cosmologically improbable window, by beings improbably situated to understand what they are recording, or it cannot be made at all. The archive is not a project for a future civilization with better tools. It is a project for the civilization that currently has access to the evidence, which is this one, in this era, before the light goes. The sixth theory is not about the future at all. It is about right now, and specifically about whether right now has happened before, whether it will happen again, and what that means for every moment you have ever survived. The math here is precise, and it has no good news version. Theory 6. Poincaré recurrence. It has no good news version. Henri Poincaré proved in 1890 that a mechanical system with a finite phase space, a system whose state can be described by a finite number of variables, each taking values in a bounded range, will, if it evolves long enough, return to any previous state to within an arbitrary degree of closeness. It is a mathematical theorem, proved rigorously, accepted by physicists immediately. Given enough time, every configuration recurs. This seems, at first, like an interesting mathematical fact about abstract systems. Then you apply it to the universe. If the universe has a finite phase space, which is consistent with some formulations of quantum gravity and with the holographic principle, which suggests that the information content of any region of space is bounded by its surface area, then every possible configuration of matter and energy in that volume will eventually recur, not approximately, with mathematical precision. This includes the configuration of matter and energy that currently constitutes the room you are in, the specific arrangement of atoms, the pattern of neural activity in the brain doing the reading, the exact quantum state of every particle in the system that is you right now. All of it will recur, in a future so distant as to be genuinely incomprehensible, but in a future that, given infinite time, is not just possible but guaranteed. Boltzmann understood this and found it troubling. It seemed to contradict the second law of thermodynamics. If entropy always increases, how can the system return to a low entropy state? The resolution is that the recurrence time is so astronomically large that it is irrelevant on any physically meaningful timescale. The second law is not violated. It describes the overwhelming probability of the short-term direction, while the recurrence describes what happens in a time frame that makes the age of the universe look like a rounding error. But in infinite time, even this timescale is passed. The recurrence happens, then it happens again. It is worth pausing here on the connection between Poincaré recurrence and the Boltzmann brain, because the two theories are not unrelated. Boltzmann himself understood that his statistical mechanics implied recurrence, and he spent much of his career trying to reconcile the directionality of time with the reversibility of the underlying equations. If any configuration recurs, then the low entropy state of the early universe, the ordered, hot, compressed initial condition from which everything expanded, must also recur. And if low entropy states recur at random, they will sometimes recur in the form of a complete false universe, assembled by fluctuation rather than in the form of a genuine beginning. The Boltzmann brain and Poincaré recurrence are the same machinery operating at two different scales. One recurs a mind, the other recurs everything the mind ever lived inside. This does not mean the theories reinforce each other as threats. What it means is that they share a common source, the statistical structure of a sufficiently old universe, in which every configuration that can occur will occur, and in which the long timescales involved make every merely improbable event into an inevitability. The arrow of time is real in the short run. In the long run, it dissolves. What cannot recur, what the physics specifically excludes, is memory of the interval. Each recurrence begins fresh. Each instance of this night begins with no knowledge of having happened before. The repetition is indistinguishable from singularity, from the inside. And so the question of whether this has happened before is not a question the current instance of you can answer. It can only be answered by the mathematics, which says, yes, an unknown number of times, with the next recurrence at an unknown distance. The implication of Poincaré recurrence for personal existence is the most complete version of repetition that any framework, philosophical or physical. If the universe returns to a state arbitrarily close to its current state, then every configuration of matter that exists right now will exist again, not approximately to within whatever degree of precision you choose. The neural configuration that constitutes your current thoughts, the specific arrangement of neurons that generates the experience of receiving these words at this particular moment, with whatever particular mood and weariness and alertness you carry tonight. That configuration will recur. Every quantum state of every particle in the system that constitutes your current mind will take those values again in a universe that has aged through everything between now and then. That future mind will have no memory of the interval. The recurrence is not a continuation. It is a new instantiation with the same state, which is, in any framework where subjective experience is determined by physical state, indistinguishable from the original. The you that recurs will believe it is experiencing this moment for the first time, just as you believe you are experiencing it now. Nietzsche, in 1882, proposed a thought experiment he called eternal recurrence, the idea that every moment of your life would repeat infinitely, and the question of whether you could affirm this. He presented it as a test of attitude. The philosophy was doing the work. What Poincaré recurrence adds is the physics. The eternal recurrence is not a thought experiment. Under the relevant assumptions, it is a theorem. And every moment recurs. Not just the moments worth returning to, every moment of confusion, of loss, of grief, of the particular weight that settles in the last hours before sleep, when the day has been long, and the distance between where you are and where you wanted to be feels sharper than usual. Those moments will recur as many times as this one will, with no editing and no softening of distance. The universe does not select the moments worth repeating. The particular difficulty of Poincaré recurrence, as opposed to simply a long future, is what it does to the concept of rarity. If you have experienced something that felt singular, a specific grief, a specific moment of clarity, a specific configuration of circumstances that seemed to belong only to you. Poincaré recurrence says it was not singular. It has occurred before, in recurrences prior to this one, in futures of past cycles of the universe that have already completed. It will occur again, in future cycles, indefinitely. The sense of singularity is a property of memory and self. It is not a property of the moment in the cosmos. Most versions of cosmic perspective make the human small. The universe is vast. You are tiny. Your concerns register at no cosmic scale. That framing is, for many people, ultimately peaceful. The smallness feels like freedom. The indifference of the universe feels like release. You might expect Poincaré recurrence to follow this same template. Infinite time, infinite repetitions, any given moment, infinitely diluted, and therefore infinitely meaningless, and therefore strangely free. It doesn't work that way. The recurrence doesn't dilute the moments. It returns them, complete, in full, the way you experienced them the first time, before the distance made them bearable. Poincaré recurrence does something different from every other cosmic perspective you've been offered tonight. It takes the moments that mattered, specifically the ones that mattered most, and says, they will all come back, not as memory, not as echo, as experience, as the first time. The night of the worst loss you have experienced will recur, complete, without the softening of distance that the original has now acquired with time. The confusion of the worst period of your life will occur again, in a mind that has not yet learned what you learned from it. The accumulated understanding that makes the past bearable will not be present at the recurrence, because the state of the mind at the recurrence is the state of the mind that had not yet passed through. There is no solution to this problem, because it is not a problem with a solution. It is a feature of thermodynamics and the geometry of state space, and it follows from mathematics that is not in dispute. The recurrence time is so large that no physical process could preserve any record from one cycle to the next. Every civilization, every archive, every signal propagated by any intelligence, all of it dissipates before the recurrence time is reached. The next cycle begins, as far as physics is concerned, fresh, and the moments begin again. What makes the Poincaré recurrence time genuinely hard to hold in mind is not that it is large. It is that it is large in a way that breaks the usual tools for scale. When cosmologists talk about the age of the universe, 13.8 billion years, there are ways to anchor that number. The Milky Way formed roughly 10 billion years ago. Life on Earth began roughly 4 billion years ago. The entire span of recorded human history occupies the last 10,000 years. These numbers can be related to each other, and the relationships give a sense of proportion. When cosmologists talk about the heat death of the universe, the timescale is roughly 10 to the 100 years. This is vast beyond intuition. But there is still a framework. It is roughly 10 to the 90 years after all the protons have decayed, roughly 10 to the 67 years after the last stellar remnants have dissipated. There is a sequence of events with known timescales, and the heat death sits at the far end of that sequence. The Poincaré recurrence time is 10 to the power of 10 to the power of 118 years. This is not simply a large number in the same category as the others. The heat death timescale, 10 to the 100 years, is a 1 followed by 100 zeros. The recurrence timescale is a 1 followed by a number of zeros that is itself a 1 followed by 118 zeros. The recurrence timescale is not larger than the heat death timescale in the way that a mountain is larger than a pebble. It is larger in the way that all the pebbles on Earth are larger than a single hydrogen atom, except the ratio is more extreme, by exponents, than any physical comparison can capture. In that time frame, the universe will have done everything it can do, in every possible order, an incomprehensible number of times. Every galaxy that ever formed will have formed again. Every star that ever burned will have burned again. Every mind that ever thought these particular thoughts will have thought them again. Not because the universe remembers, because the universe has time enough to arrive at every configuration by random walk, without any memory, without any direction, simply by persisting. And still, tonight is the one you're in. The seventh theory is the most technically precise of the 8, and for that reason, the most difficult to hold. It describes something that the universe may contain right now, in multiple locations. Places where the equations of physics do not produce a number. Not the wrong number. No number. The calculation halts, and what happens next is not determined by anything that came before. Theory 7. Naked singularities. It requires care to understand, because what it describes sounds like hyperbole, and it is not hyperbole. Somewhere in the universe, possibly in multiple locations, there may exist regions of space-time in which the equations of general relativity do not give a result. Not a wrong result, not an approximate result, no result. The mathematics produces infinity where it should produce a number, and infinity is not a number physics can use. The calculation halts. The future of a system near these regions cannot be determined from its past by any equation, no matter how accurate. These regions are called naked singularities. And whether they exist is one of the longest-standing open questions in classical general relativity. Roger Penrose proposed the cosmic censorship conjecture in 1969, which states that naked singularities, gravitational singularities not enclosed within event horizons, cannot form from regular matter under physically reasonable conditions. The conjecture followed from a concern. Inside a black hole, singularities are believed to exist, but they are hidden behind an event horizon. The singularity is censored from the rest of the universe. Its pathological behavior cannot propagate outward. A naked singularity would have no such protection. It would be visible in principle from outside, influencing regions of space-time causally connected to the rest of the universe. The problem with naked singularities is not that something unusual happens near them. The problem is that causality, the requirement that each state of a system has a determinate cause in its past, fails near them. Events can occur that have no cause in the sense that physics can describe. The evolution of the universe in the vicinity of a naked singularity is not uncertain in the way quantum mechanics is uncertain. Probabilistically undetermined, but well-defined. It is undetermined in the stronger sense that no equation can predict what will happen next, because the influence of the singularity introduces a term that is not mathematically well-defined. Penrose conjectured that nature prevents this by always hiding singularities inside black holes. The conjecture has never been proven. Despite 50 years of effort by some of the most sophisticated mathematical physicists in the world, it remains a conjecture. The numerical simulations that probe naked singularity formation have produced deeply ambiguous results. In 1991, Matthew Choptuik, working at the University of Texas, simulated the collapse of scalar field configurations near the critical threshold between forming a black hole and dispersing. At exactly the critical threshold, the resulting spacetime contained a naked singularity, not as a simulation artifact but as a mathematical feature of the exact critical solution. The result was published, discussed widely, and did not resolve the censorship conjecture because the critical point requires infinitely precise fine-tuning. No physical process is expected to hit exactly the critical threshold. But subsequent work found configurations that appeared more physical. Pankaj Joshi, at the Tata Institute of Fundamental Research, spent decades constructing solutions to Einstein's equations that produced naked singularities from smooth, regular, initial conditions without requiring fine-tuning. His work appears in mainstream general relativity journals and suggests that cosmic censorship may not hold in all physically relevant cases. The implication, if his work is correct, is precise and strange. There exist regions of space-time in which the equations of physics stop working, not in the interior of a black hole, where the stopping is hidden. Visible regions that exert influence on their surroundings. Regions where the laws governing how matter and energy evolve break down in a way that propagates causally outward. Here is the part that is not hyperbole. Near a naked singularity, it is not that something rare or extreme happens. It is that the concept of because stops applying. The sentence, "This happened because of that," the foundational sentence of every causal explanation in all of physics, stops being meaningful in a geometrically defined neighborhood of these objects. The universe, in those regions, is not computing its own evolution by rules. The rules break. Not at an inaccessible interior, in a region that is in causal contact with the rest of space-time. The universe, if it contains naked singularities, contains places where physics does not apply, not places where physics is hard, places where it stops. Physicists who work on this problem are careful to note that naked singularities, even if they can form, would be rare and localized. The collapse configurations that produce them are not common. They do not threaten the everyday operation of physics across the vast majority of space-time. The laws you rely on for chemistry and biology and everything else continue to work in the regions that matter for life. What they cannot say is that naked singularities don't exist. The cosmic censorship conjecture remains a conjecture, a widely believed expectation, supported by many special cases and motivated by strong physical intuition, but not a theorem, not a law. Quantum gravity, the as yet undeveloped theory that reconciles general relativity with quantum mechanics, may change what singularities are and whether they remain as pathological as the classical theory suggests. Some approaches to quantum gravity replace singularities with regions of very high but finite curvature, which would be extreme but potentially calculable. If this is right, the naked singularity problem dissolves into a quantum gravity problem, which at least has a different character. But quantum gravity is not done, and general relativity, as it stands, does not guarantee that causality holds everywhere. There are places in the universe, or there may be places, which is the same for most practical purposes, where the sentence "because it happened before" stops being a valid explanation. where the past does not determine the future in any mathematically well-defined sense, where the universe is not computing its own evolution, where there are no rules. We do not know if we live near one. We do not have a theorem that says we can't. The most we can say is that the physics of the regions we can observe appears to work. The regions we cannot observe are under no obligation to be the same. There is a concept in general relativity called global hyperbolicity, a technical condition a spacetime must satisfy in order for physics to be predictive at all. A globally hyperbolic spacetime is one where, given the state of a physical system on a single surface of constant time, the equations of motion can determine the state of that system at any other time. The past determines the present determines the future. Causality holds everywhere. General relativity guarantees global hyperbolicity only under specific conditions. One of those conditions is the validity of cosmic censorship. If singularities can be naked, if they can influence external spacetime without being shielded by event horizons, then global hyperbolicity fails. The universe ceases to be predictive in the neighborhood of such a singularity. The equations of motion run up against a boundary they cannot cross. Not because the physics is too complicated, but because the physics is genuinely absent. What this means practically is that the universe may contain regions where the act of prediction is not merely difficult but meaningless. Not regions where we lack good enough instruments. Not regions where the complexity exceeds our computational capacity. Regions where the causal structure of spacetime itself prevents the future from being determined by the past in any well-defined sense. Joshi describes the naked singularity as a window to the initial singularity, a place where the extreme physics of the Big Bang, normally hidden from the present universe by billions of years of expansion, is somehow exposed again. A local analogue of the beginning, a region where densities become so extreme and space-time curvature so large that the ordered evolution of physics, according to smooth equations, runs into the same kind of boundary it ran into at the very beginning of time. We are, in most of the universe, far from such boundaries. The cosmos is old and dilute and calm at the scales relevant to life. The nearest black hole is several thousand light-years away. Naked singularities, if they exist, are likely associated with stellar remnants at conditions far beyond anything in our local neighborhood. But the existence of such boundaries, the possibility, not yet ruled out, that the universe contains places where prediction fails and causality bends, changes something about the picture. The universe is not uniformly governed. It may be a universe with exceptions, with seams, with places where the weave of physical law becomes thin enough to see through. We don't live near any of those places, but we share the universe with them, if they exist. And sharing a universe with places where causality fails is a different kind of place to be than one where the rules hold everywhere, without exception. The particular discomfort of this, the specific quality that distinguishes it from the other 7 theories, is that it is not a threat to your existence, or your history, or your knowledge. It is a threat to the completeness of the framework. The false vacuum threatens what the universe is made of. The Boltzmann brain threatens what you are. Quantum immortality threatens what will happen to you. The anthropic shadow threatens what you can know about your safety. The last stargazer threatens what future minds can know about the cosmos. Poincaré recurrence threatens the uniqueness of your moments. Naked singularities threaten something more foundational than any of these. They threaten the assumption that the universe is, in every corner of itself, a place that follows rules. We operate, in ordinary life and in science, on the premise that the universe is consistent, that the equations we have derived describe something real, and that the something real they describe extends everywhere, not just to the regions we can easily observe. Physics is global. The laws are universal. The fact that we have never observed an exception is the evidence we use to extrapolate the rules into the unobserved regions. What cosmic censorship conjecture failure would mean is that this extrapolation is wrong, Not in a minor way, not in the way that Newtonian mechanics was wrong when relativity corrected it, but wrong in the sense that there exist places in the universe where the machinery of rules genuinely does not operate. Not rules we haven't found yet. No rules. The future of a physical system near a naked singularity is not determined by any past, any equation, any principle. It simply occurs. This is not physics as we know it. This is the universe having holes in it. The eighth theory is the last. It is different from all the others in a specific way. It is the only one that isn't a threat. It is simply a reason why the universe is quiet. Theory 8. The aestivation hypothesis. The aestivation hypothesis was published in 2017 by Anders Sandberg, Stuart Armstrong, and Milan Ćirković in a paper titled "That is Not Dead, Which Can Eternal Lie: The Aestivation Hypothesis for Resolving the Fermi Paradox." The title is a reference to H.P. Lovecraft. The content is thermodynamics. The argument begins with a basic fact about computation. Every computational operation, every bit flip, every logical operation, every process that changes information from one state to another dissipates energy as heat. This is Landauer's principle, established in 1961 and empirically verified. The amount of energy dissipated is proportional to the temperature of the environment. The hotter the environment, the more energy you lose per operation. The colder the environment, the more efficiently you can compute. This is not a limitation of technology. It is a fundamental thermodynamic constraint. Any civilization that thinks, that models the world, that pursues any goal requiring information processing, is subject to Landauer's principle. In a hot universe, computation is expensive. In a cold universe, it is cheap. The universe is currently cooling. It will continue to cool. The cosmic microwave background temperature, currently about 2.7 Kelvin, will continue to decline as the universe expands. In 1 trillion years, it will be a fraction of a degree. As it approaches absolute zero, the cost of computation approaches the physical minimum, smaller by an astronomical factor compared to today. A civilization that has reached technological maturity, that has access to essentially all the energy available from its galactic neighborhood, faces a specific choice. It can use that energy now, computing and thinking, and creating at the maximum rate its current thermal environment allows, achieving some large but finite amount of computation before the stars go dark. Or it can wait, convert its available energy into the most stable, long-lived storage form possible, shut down all non-essential processes. I estivate the technical word for dormancy in the heat, as opposed to hibernation in the cold, until the universe has cooled enough that the same energy produces exponentially more computation. Sandberg, Armstrong, and Ćirković calculated the advantage of waiting. The ratio of computation achievable in the cold future versus computation achievable now, using the same energy budget, is approximately 10 to the power of 30. A civilization that waits gains the equivalent of a factor of 1 billion times more thought, more experience, more existence for the same investment, under any reasonable assumption about what advanced civilizations value. More experience, more knowledge, more of whatever they are. Waiting is not merely rational, it is overwhelmingly optimal. The Fermi paradox, the observation that the cosmos appears empty of intelligent life despite its vast age and size, has generated dozens of proposed solutions. The Great Filter, the zoo hypothesis, the dark forest theory, various forms of the rare earth hypothesis. Each one attempts to explain the silence with some claim about why civilizations don't or can't or won't communicate. The aestivation hypothesis offers an answer that doesn't require civilizations to die or to choose silence as a moral position. They are here. They have always been here. They are waiting in the dark, with their energy stored, their processes paused, their vast computational capacity suspended in the most efficient storage medium their physics allows, waiting for the universe to cool enough to be worth running. The universe is currently about 13.8 billion years old. It will produce stellar populations, new stars, new energy sources, for roughly another 100 trillion years. After that, the remaining matter slowly cools over timescales that make the stellar era look brief. An advanced civilization that wants to maximize computation would begin its dormancy at approximately the stellar era, around now or in the near future by cosmic standards, and wait until temperatures approach the lowest achievable values, perhaps trillions of years from now. From our position, such a civilization would be completely invisible. It has shut down active processes to minimize energy expenditure and avoid detection by anything that might want to compete for its resources. Its hardware, whatever form its physical substrate takes, generates no waste heat worth detecting. It emits no radio signals. It undertakes no megastructure construction, because megastructures are detectable. It does nothing that could distinguish it from a collection of cold, dense, inert matter. There is cold, dense, inert matter everywhere. The dark matter halos surrounding every galaxy, whose gravitational effects we measure, but whose composition remains unknown. Some fraction of that mass could be the stored hardware of sleeping civilizations. Not all of it. Probably not most of it. But physics does not prohibit it. There is no observation we have made that rules it out. The silence that cosmologists have interpreted as absence may be, in some fraction of cases, the silence of an enormous intelligence holding its breath. The specific quality of the aestivation hypothesis is not that the civilizations are hostile. The hypothesis makes no claim about their intentions. It is that they are present in a way that makes presence indistinguishable from absence, and that when they wake, if they wake, the universe will be a fundamentally different place. An estivating civilization that wakes in 10 trillion years finds itself in a universe that has cooled dramatically, with vastly more efficient computation available, with an energy budget preserved across an almost incomprehensible span of dormancy. The stars that existed when it slept are gone. The civilizations that arose during its dormancy, civilizations like whatever we will have become, or failed to become, are either gone as well, or themselves dormant, waiting for the same cold future. What a waking civilization does with its vast computational resources is not specified by the hypothesis. It might compute, it might simulate, it might interact with whatever remains of the physical universe in ways not predictable from inside the current epoch. It might not interact at all. Having decided that the universe it runs inside its own substrate is more interesting than the universe outside. What the hypothesis does specify is that the silence surrounding us is not the silence of empty space. It may be the silence of patience. The universe may be full of minds that are simply on a different schedule, one that makes the entire history of Earth from the first cell to the last human look like a brief flicker in the period before the real waiting began. The discomfort is purely existential. We may be shouting into a room full of presence that has simply chosen not to answer, because answering would cost energy not yet worth spending, in a universe not yet cold enough to make the answer worth its price. We will not live to see the response. The aestivation hypothesis is, in a sense, the gentlest of the 8 theories. It does not end the world. It does not fabricate your memories. It does not trap you in immortality, or remove the evidence of your cosmos, or make causality a local phenomenon. It simply says, the room is not empty. The room is full, but the fullness has a specific quality that the others don't. Every other theory on this list is something that happens to you, or to the physics around you, or to the evidence available to you. The aestivation hypothesis is something that is happening alongside you. At this moment, as you are lying in the dark thinking about these 8 things, there may be something else in the dark, something that has been there since before any star in the Milky Way formed. Something that chose patience over presence, not out of indifference to us, but out of the simple calculation that the universe isn't cold enough yet for the work it has been waiting to do. And the universe we are in is not cold enough yet. We are the noise before the computation begins. We are the warmth before the cooling that makes the real computation possible. We are a brief turbulence in a process that is mostly waiting. And we happen to be the part of the process that is awake and asking questions. And the questions we are asking are pointed at the sleeping part, and the sleeping part does not answer. Not because it doesn't know we're here, but because answering, in the current thermal environment, is not worth the cost. This is not threatening. It is the most peaceful framing of the silence that any cosmological theory has produced. The universe is full. It is simply not awake yet, and when it wakes, in the cold, patient dark, in the unimaginably distant future, it will begin the work it has been waiting to begin since before we were born. Between now and then, us, this, tonight. The aestivation hypothesis is ultimately a hypothesis about the relationship between intelligence and time, specifically about the question of when to be. Most of the ways we think about consciousness, about the value of experience and thought, assume that earlier is better, that being conscious now is straightforwardly preferable to not being conscious now, that a life deferred is a life diminished, that the purpose of intelligence is to engage with the present. The aestivation hypothesis suggests that a sufficiently advanced intelligence might arrive at the opposite conclusion, that engaging with the present is costly in a way that engaging with the future is not, that the same energy, the same computational substrate, the same capacity for experience and thought, all of it can be multiplied by an astronomical factor simply by waiting for the universe to cool. That deferred consciousness is not diminished consciousness, but maximized consciousness. If the measure is the total volume of experience rather than its temporal location, this is alien to how we think about being alive, which is understandable. We are biological systems that evolved to occupy a present. Our minds are built around continuous engagement with sensory experience, emotional state, social connection, all of which require being awake, being present, being in the moment, in a literal and not merely rhetorical sense. But the mathematics doesn't care about our evolutionary priors. The mathematics simply describes what happens to computation efficiency as temperature decreases, and the result is unambiguous. Waiting is better. If what you value is computation, waiting is better. If what you value is experience, waiting is better by a factor of 10 to the 30. If what you value is being able to think as many thoughts as possible before the energy runs out. And so, if the hypothesis is correct, the universe is mostly waiting. The civilizations that are here, existing in this universe at this moment, have judged that now is not the time to be fully awake, that the epoch in which we find ourselves is the warm season, the expensive season, the season in which being awake costs more than it will be worth, and they have stored themselves against the cold, and they have gone quiet, and they are patient in a way that nothing built on biological wetware and 100-year lifespan can fully comprehend. Between us and the waking, everything, every star that has not yet been born, every galaxy that will not yet form, every civilization that will arise and estivate in the trillions of years between now and the epoch, when the cost of thought approaches its minimum and the stored minds, one by one, come back online into a universe that is cold and quiet and patient and very, very old. We are, in that picture, a very early morning. The real day has not yet begun. There is something in this picture that is difficult to situate in ordinary experience, but worth sitting with. Every civilization that has ever existed, every intelligence that has ever asked any question, every mind that has ever worked through the kind of reasoning that produced these 8 theories, all of it occurred in the warm season, in the era of active stars, of abundant energy, of computation that was expensive relative to what the cold future will make possible. The warm season has been running for approximately 14 billion years, and it will continue for roughly another 100 trillion. That is an enormous span. By any historical measure, it is incomprehensible, but it is a fraction of 1% of the time that the cold future occupies. And the cold future is where the overwhelming majority of the potential computation waits. The sleeping civilizations are not missing the good years. They are, by the thermodynamics of the calculation they ran, skipping past the expensive years to get to the good ones. The warm season, which contains everything any biological mind has ever experienced. Every war and discovery and question and night like this one, is, in the context of the full temporal budget of the universe, something closer to the throat clearing before the speech begins. If this is right, then the universe is not wasted in its current state. It is being stored. The energy that powers every star, every planet, every biological process, every thought, all of it will eventually be available for conversion into the most efficient computational work that thermodynamics permits. Not now, not in any era a biological mind will inhabit, but the conversion is already being planned by intelligences that are already old, already waiting, already certain that the universe will cool as the physics says it must, and that when it does, the work they have been waiting to do will become possible in a way it is not possible today. We are, in that picture, a very early morning. The real day has not yet begun. 8 theories, all verified, or at least unrefuted, all mathematically clean, all pointing in the same direction toward a universe that is stranger than the strangeness we reach for when we want to feel appropriately small. We have been through the false vacuum, which makes the stability beneath us a local condition rather than a law. The Boltzmann brain, which makes your history a statistical improbability rather than a certainty. Quantum immortality, which makes death inaccessible from your own perspective. The anthropic shadow, which makes our survival evidence not of safety but of selection. The last stargazer, which makes the evidence for the universe itself temporary. Poincaré recurrence, which makes this moment a recurring event rather than a singular one. Naked singularities, which make causality a regional phenomenon rather than a universal one. And the aestivation hypothesis, which makes the silence of the universe not emptiness, but patience. None of these are speculations. They are mathematical results, physical derivations, published conclusions. The flaws have been looked for carefully by people whose entire professional identity is built around finding flaws in exactly this kind of reasoning. Most have not been found. What they share is not a mood. They are not a collection of dark thoughts assembled to unsettle. They are different aspects of the same underlying structure. The universe at its deepest level is not arranged around us, does not prioritize our continuity, does not guarantee the stability we depend on, and does not preserve the evidence we need to understand it. It simply operates, following rules that are consistent and in some cases verifiable, producing as a byproduct the particular configuration of matter and time in which minds like yours exist and ask questions like the ones these theories try to answer. That is not a tragedy. That is a description. And within that description, within the false vacuum and the Boltzmann brain and the sleeping giants and the recurrence, there is something worth noticing. The universe did not need to produce minds capable of deriving these theories. The physics of the Higgs field does not require consciousness to function. The equations governing quantum tunneling have no provision for the existence of organisms that can write them down. The laws of thermodynamics were doing exactly what they do for 9 billion years before the Earth formed, and for another 4 billion years before any arrangement of matter on this planet developed the neural complexity to ask what the laws of thermodynamics implied about its own existence. That question, this question, the one that produced these 8 theories, was not required by the universe. It was something the universe happened to produce. The way it happens to produce supernovae and gravitational waves, and the particular chemistry of water. A local event in the long, slow process of everything becoming something else. You are lying in the dark in a universe that allows all 8 of these things to be true simultaneously. The same universe that produced the Higgs field and the probability of tunneling and the thermodynamics of thought produced, first, the conditions for water and carbon and neural tissue, and the long, improbable climb from chemistry to consciousness. Whatever you are, Boltzmann fluctuation or evolved observer, mortal or branching survivor, alone in a universe emptying itself of evidence, or surrounded by sleeping giants in the dark, you are here now, thinking now, in a configuration that the physics permits, however briefly, however precariously. Right now, outside wherever you are sleeping tonight, the laws of physics are holding, or they are not holding, and the bubble is close enough that the distinction no longer matters. Either way, the night is still the night. The air is still the air. The particular quality of darkness behind your closed eyes is still yours. The 8 theories do not resolve each other. The universe is not obligated to be consistent across these different levels of analysis. And it shows no sign of caring whether its deeper implications make sense together. The vacuum can be false while the Boltzmann probability is real, while the branches are all simultaneously actual, while the evidence for all of it is slowly redshifting away from every future observer. These are not competing truths. They are layers, each operating at a different scale, each following its own mathematics, all of them describing the same place. Here, that has always been all we had. What is strange, and worth sitting with as you drift towards sleep, is that the 8 theories don't make this less true. They deepen it. A universe that could end without warning, that may have assembled your consciousness seconds ago from random matter, that may contain sleeping minds in the dark, and places where causality fails and futures already lived, and stars that will burn as evidence of a history no one will be able to read. That universe still produced this particular night, this particular hour, this specific configuration of matter that is you, receiving these words, drifting towards something quiet and dark and very old. It was always enough. If your eyes feel heavy, let them close. The universe has been running these calculations for 14 billion years. It will continue without your supervision tonight. If this felt like something worth returning to, leave a comment when you wake up. The universe will still be here when you wake up. So will we. Good night.